This video is about the descending limb of the Starling curve. The Starling curve is also called the Frank-Starling curve or the Frank-Starling mechanism. So the Frank-Starling mechanism is the physiological relationship where increasing filling of the heart or preload results in an increase in cardiac output or stroke work. So the so-called descending limb of the Starling curve is a part of the curve where that normal physiological operation actually reverses. An increasing preload might actually reverse and result in a decreasing in output or stroke work with increasing preload. So that might seem like a kind of esoteric topic. It probably is. But in any event, I'm going to try to show you that the question of the existence of the so-called descending limb may actually be important in how we think about treating heart failure. It's something that folks have been arguing about for almost 100 years. So, I mean, somebody must think it's. But anyhow, okay, so a little bit of background. The Starling law, the Frank-Starling law, it's fundamentally important in cardiovascular physiology. It's pretty straightforward. It says that the more blood with which you fill the chambers of the heart and diastole, and that's called preload, okay, the more stroke volume you get and or the more cardiac output. Okay, so the amount of diastolic filling is called preload. The relationship between the preload and either the stroke volume or the cardiac output is often plotted as the right atrial pressure versus stroke volume or cardiac output. So the right atrial pressure is the filling pressure on the right side of the heart. And that's because as the filling pressure goes up, the amount of filling goes up. So sometimes right atrial pressure or not sometimes, very often right atrial pressure is a proxy for preload. So as an aside, Frank here certainly deserves more of the credit for the concept than Starling, even though Starling probably gets more of the credit. In fact, the basic ideas underlying the phenomena actually predate both Frank and Starling. Starling is almost certainly purposefully, it seems like, failed to credit Frank. The history has actually been reviewed in the past, and this paper here is a nice review of the history if you're interested. The goal here is not to go through that history, but we do want to understand the origin of the so-called descending limb. So we have to go back in time a little bit to 1914. So this is a diagram here on the left from Starling and Patterson's 1914 paper. And this is a diagram of their so-called heart-lung preparation. Their experiment was really important in developing an understanding of things because they could independently control preload to the right side of the heart, and afterload, the pressure in the large arteries or the aorta coming out of the left side of the heart. So this is how the system worked. And their experiments were done in dog, while a lot of previous work was done in frogs. And so the fact that they studied a mammalian system with a 4-chambered heart probably enhanced the clinical relevance of their findings. Anyhow, they cannulated this carotid artery, I guess the first carotid artery, the right carotid artery, which is the first one to come off the aorta. They occluded the aorta, so all the blood ejected from the ventricle went through their circuit here. It went through their circuit into this heating element where the blood was heated to maintain body temperature, and then it was pumped into this reservoir. Okay, and this reservoir could be raised or could be lowered to give you different driving force with gravity. So they had manometers connected to the right atria, okay, to the left atria, to the aortic pressure here. And they had a, this variable resistor, called a Starling resistor, and now it controlled the afterload. And they could control the preload either by raising and lowering this reservoir and or by changing the resistance across this clamp here for this preload resistor. Okay, I'm showing over here on the right this diagram of the coronaries because just to point out something important that even with the aorta tied off here, the coronaries come off of the main trunk of the aorta, well before that, where they cross clamp the aorta. So the heart remains perfused Okay, and so what's happening is the blood comes out of the left ventricle through the aorta, travels through the circuit here, and comes back through to the right-hand side. Okay, so that's a little complicated looking. Here's a simplified view of their setup. Okay, so the heart and lungs are cut off from the rest of the body. Okay, and so the body, and so if you look below, here's their preparation. So the body is replaced with this circuit, and they've got this resistor controlling afterload. They've got this reservoir controlling preload, and everything comes back to the heart and lungs. Okay, on the right here, these are the data from their 1914 paper, and the axes are switched from what we just saw a minute ago. Here, this is the right atrial pressure here on this axis, and here's the output, the flow, the cardiac output on this axis. And as the right atrial pressure increases, these are all data from individual dogs, the cardiac output tends to increase. Okay. They didn't really do a systematic study here, but the claim is that the result is basically the same, whether or not they keep the afterload pressure constant by adjusting that Starling resistor, or they keep the resistance constant and let the afterload increase with increasing cardiac output. So the important thing is, as the curve goes up, as the right atrial pressure goes up, the output goes up, and that's the Frank-Starling mechanism. But sometimes the curve kind of turns around here, right? And this turning around happens at pressures that aren't so astronomically high, maybe 20 or 10 millimeters of mercury, which aren't so unreasonable physiologically. So this turning around is the descending limb, and the question is it real? If it's real, when does it happen? Why does it happen? So first off, let's see what Starling had to say about this. So Starling says that in the distended heart, so this is the heart that's really filling up with a lot of preload, tension in the muscle fibers will rise more rapidly than intracardiac pressure. The more distended the heart, the greater will be the mechanical disadvantage under which the muscle fibers act. This ever-increasing disadvantage must finally result in a condition in which the muscle fibers are unable to contract at all or raise the pressure higher than exists at the end of diastole. So the heart's action must come to an end. So what he's talking about, I think, he doesn't really talk about the law of Laplace, but and I went through his famous Lineker lecture on the law of the heart, and he didn't exactly invoke the law of Laplace in that either. But conceptually, what he's talking about is, if you have, some kind of a geometry like this, you can think of and this is the heart wall, right? And then inside here is the lumen of the ventricle, say the left ventricle, right? Let's call the thickness here of this wall W. Let's say you're generating some pressure inside this chamber, call it P, and the diameter of this thing is D for diameter. Okay, and something called the law of Laplace tells us that the amount of stress in the walls needed to generate a given pressure is proportional to that pressure, which makes sense. So more pressure, more stress, times diameter divided by the wall thickness. So if you had a really dilated kind of heart, you filled it up a lot, okay? Well, you take this initial geometry here and fill it up. The wall thickness is going to go down, and the diameter is going to go up, right? And so what that means is, the big D and small w, the amount of active stress, or sigma, in this equation, you needed to develop a certain amount of pressure would get really high. Okay, so this is not what's happening in Starling's experiments, by the way. So in a normal heart, you're not going to get enough feeling for this relationship to explain the Starling descending limb. But what we're seeing here in this relationship actually becomes important if the heart were to chronically remodel to a dilated state with a large diameter, small w, and a really dilated geometry. The ability to actively generate pressure is impaired. And so that impairment is part of what's going on here in these plots of the Frank-Starling mechanism for normal versus failing hearts. So this is from the very useful Lilly textbook. Yeah, here it is, cited down here. Okay, and you can see in this diagram, so here's the normal, here's failing. There's no descending limbs. Okay, but this graph is showing a few things. So first of all, the Starling curve and failing heart failure is depressed, right? And so with the depressed Starling curves, one of the fundamental ways that the body responds is by a compensatory increase in preload. So that increase in preload happens via a whole number of different mechanisms. First off, if the cardiac contractility were suddenly drop, think about something happening acutely like a myocardial infarction, that consequential drop in cardiac output and in arterial pressure would be associated with a shift of volume to the venous side of the circulation, resulting in an increase in preload, okay? There'd also be an autonomic response, increasing venous vasoconstriction. So both of these things are going to increase preload. And so increasing preload you can think of as compensation because you're moving up the Starling curve as you increase preload, right? So on longer time scales, autonomic and endocrine systems can work together to retain volume in a failing heart, leading to increased interstitial, lymphatic, and venous pressures, and a congested state. Okay, so there's that word congestion. So with high venous pressure, particularly in the pulmonary venous pressure, you're going to get filtration out of the pulmonary capillaries, buildup of fluid in the lungs. Okay, and there's all kinds of negative consequences of pulmonary congestion. And so one of the goals of therapy in heart failure is to unload that excess volume with diuretics. And that's actually, there's something that's always bugged me about pictures like this in textbooks, and that is by relieving congestion, you might be doing some good things, but you're also moving down the Frank-Starling curve, which is what's illustrated here in this diagram. So what Lilly says is that's okay as long as you know what you're doing. Decongestion with diuretics will not significantly reduce stroke volume and cardiac output in this setting because the failing ventricle is operating on the flat portion of the depressed Frank-Starling curve. Okay, and that's kind of what they're showing with these different arrows. In fact, so this is going from A to B is what might happen if you relieve congestion by giving a patient Lasix and a patient pees off a lot of volume. What's happening in these other arrows is what you might be able to achieve by combining positive inotropes with diuretics. Okay, so the diuretic might move you down the curve a bit in the left, going to the left, but you can make up for it with an inotrope. Yeah, okay, now, and I'm not a cardiologist, but I believe that the situations in which you would treat a heart failure patient with positive inotropes are actually pretty few and far between. In fact, according to this very same Lilly textbook, the use of positive inotropes is extremely limited clinically and actually usually counterindicated. On the other hand, just about all systolic heart failure patients are put on beta blockers, which have negative inotropic and chronotropic effects. So anyhow, I think this diagram would be a lot easier to interpret if there were a descending limb, right? Like this. And so if a descending limb actually existed, at least in heart failure conditions, then decongestion, right, reducing preload would reduce congestion and would actually move you up the Frank-Starling curve, right? In fact, sometimes people draw these curves that way. So here, from a 1952 paper, here's a normal Frank-Starling curve, okay, and then hypodynamic or mechanically failing heart, you get a descending limb. In fact, the whole thing is descending in this example. From 1992, a critical review of the concept of the descending limb actually is criticizing McMichael's paper, saying it is doubtful whether this view is based on any well-documented observation. So wow, that's pretty harsh criticism. But the truth is, actually, if you read this review, the rejection of the descending limb is also not based on any well-documented observation. It just says it doesn't happen. So there's really no clear consensus here of what's going on. what should we do? Here on the right here, and this is from every med student's favorite reference, the first aid for the USMLE. What they do is what I think you might interpret as kind of a little bit of a cowardly equivocation. They draw the descending limb in heart failure, but they draw it as a dashed line, right? So what's that supposed to mean? And maybe it means whatever you want it to mean. So if you're a true believer in the descending limb, well, there it is for you to look at. If you're a skeptic, well, the line's dashed because it's not real after all, right? So what do the authorities have to say about all this? This is an editorial review from 1965 written by Arnold Katz, one of the great authorities on cardiac research and cardiology from the 20th century. So Katz says, examination of the laws governing the behavior of the heart in an intact animal indicates that operation of the heart on the descending limb of the Starling curve constitutes an unstable situation from which can develop a vicious cycle that could terminate rather quickly the life of the animal. I'm not 100% sure about what Katz is getting at here. It's not totally clear. I'm going to go out on a limb, pardon the pun, and try to interpret what he's saying. And by the way, I think he's wrong, and I'll show you why I think he's wrong. I invite anybody who's listening or viewing this video to correct me if I'm wrong. But here's what I think Katz is talking about. She's talking about stability analysis, and we can, look at the typical kind of plot here of cardiac output as a function of right atrial pressure. And it turns out that there's a relationship between right atrial pressure, cardiac output, and right atrial pressure, which is governed by the function of the vasculature. And so it's sometimes called the vascular function curve. And you might have seen that before. And what this vascular function curve says is that, as cardiac output goes up, that causes a reduction in right atrial pressure. And as cardiac output goes down, that causes an increase in right atrial pressure. And the reason for that is, you can imagine if the flow goes down, there's a shift of fluid to the inlet side of the pump, or the venous or the right atrial side of the pump. So that's called the vascular function curve, and we can plot that on the same plot as the Frank-Starling curve. And where those curves intersect is where the system is operating at its steady state. And the question is this steady state stable? And it's stable. You can show it's stable by doing some kind of thought experiment. You can imagine a reduction in cardiac output. And what is the how's the vasculature going to respond to this reduced cardiac output? Like I said, when cardiac output goes down, it wants to increase preload because volume is going to build up at the volume and pressure are going to build up at the inlet, right? At the same time, at this value of right atrial pressure, whether it's at this value or if it's increasing, cardiac output is going to want to go up based on the Frank-Starling curve. And if you follow what happens in time, is that anywhere you start in this two-dimensional plane, you move in towards this stable point. Okay, and that's why the system is stable. What about with this descending limb? Does the descending limb cause there's our vascular function curve. Does it cause an instability? So here's our stable point. And as long as the curves cross like this, actually it doesn't cause an instability. We can do the same kind of thought experiment. We can reduce the cardiac output. What that's going to do is going to want to make the right atrial pressure go up. And given your right atrial pressure, that's going to want to make the cardiac output go like that. And this system is going to go back here. We can start someplace else. We can start in here if we want. So now we've increased the right atrial pressure and reduced the cardiac output. So we're in between the two curves on the face plane like this. And there's going to be a vast tendency for the vasculature for preload to reduce. Okay. And there's going to be a tendency for the cardiac output to go up. And you're going to track into the same stable point. And you can start anywhere you want, and you're going to go towards that same stable point. So the system is stable as long as the Frank-Starling curve and the vascular function curve cross like this, even if the Frank-Starling curve is operating on this so-called descending limb. Okay, so there's no theoretical reason, or at least there isn't one that I know of, why there can't be a descending limb. The question, is there a descending limb, or can there be a descending limb, and under what circumstances? And it turns out that Sarnoff and Braunwald sorted this out a long time ago in the 1950s. Frankly, so why the world has remained so confused on the point, I don't really understand. But anyhow, this is what they did. So in a lot of ways, their experiment was simpler than Starling's experiment. So they kept the circulation to the body intact. I'm drawing the left side on the right side here, and vice versa. But as you know, the left side takes blood from pulmonary arteries, returning from the lungs. It pumps it out to the body. Okay, blood in the systemic veins returns back to the right side of the heart, which pumps it to the lungs, and that's the circuit. And what Sarnoff and Braunwald did is that they went through the chest and they cannulated either the left or the right atrium, and with a reservoir of blood here. And the reservoir was raised or lowered, just like in a Starling experiment, to achieve a given pressure, and the system was operated until they reached a stable, steady state. As they say over here from their paper, the preparation was equivalent to changing the circulating blood volume, by either withdrawing or infusing blood from a large vein. So the catheters in the atria allowed them to measure pressure in both, right? And here's how their experiment worked over here on the left. So as volume is infused, the pulmonary arterial pressure, the right atrial pressure, the left atrial pressure, the aortic pressure, and the total flow, the cardiac output, all go up together in concert. Okay, so the preloads, the afterloads, they all go up. And to understand the connection between the preload and the contractility, they plotted right and left atrial pressure. Okay, this is the left here, and this is the right here. Okay, left and right atrial pressure versus right stroke work or left stroke work. Okay, so remember, stroke work is the area of the pressure volume loop. So we have a left Frank-Starling curve and a right Frank-Starling curve. And so the first important point, there's no descending limb, okay, for either one of these curves. Okay, so the left here saturates, and you get up into these kind of pressures. These are centimeters of water. 35 centimeters of water is like, roughly speaking, 25 millimeters of mercury. So that's, awfully high physiologically. The right side didn't saturate, and these are just two different. Here, this is their figure one here. One animal, their figure two, different animal, and what they said is that this plateau, or what I'm calling saturation, always appears on the left. So here's a plateau on the left. Okay, on the right side, sometimes it looked very linear like this. Sometimes it was kind of curvy, but it's still not quite saturating on the right side. And it probably just has to do with the inotropic state or the specific details of the experiment for that, individual case. Okay. No descending limb. Important conclusion. But they actually had a lot to say about the descending limb. Specifically, they say the descending limb was almost never on the right and only on the left under special circumstances. And what were the special circumstances? So for our purposes, two particular kinds of special circumstances. So one is when they had really opened up the pericardium and the geometry of the heart probably got really awfully messed up. They started to get, when the preload was really high or the filling was really high, they started to see evidence of regurgitation of the ventriculo-auricle valve, or otherwise known as the mitral valve. So that's a pathological thing that was happening, and that probably explains what was happening in the Starling experiments. At least that's my understanding. So another situation that might be very important for us is what happened when they occluded supply of blood to the left side of the heart. Okay, and here's what happens when the left coronary artery is occluded. So here's the same thing we're plotting before. Here's the left stroke work versus left atrial pressure. Here's the right stroke work versus right atrial pressure. When you occlude blood flow to the left ventricle, you're diminishing or impairing its contractility, and the Frank-Starling curve goes down, and it actually bends down. The typical way, the way that Starling plotted this curve, which is cardiac output versus right atrial pressure, is down here in this smallest panel here. And you can see that when you're causing mechanical dysfunction on the left side, you get, lo and behold, a descending limb. And all of these experimental data points actually represent stable operating points of the system. So we can forget about the stability stuff I was talking about a couple of slides ago. These are actual observations. So these data are a direct disproof of at least how I'm interpreting what Katz is saying, of what Katz is saying about stability in the descending limb. And here's the important point that Sarnoff and Braunwald made. The right ventricular relationship between stroke work and preload did not change with occluding supply to the left side, right? So, control and then these occlusions are sitting right on top of each other for the most part. So as the left side failed, the afterload to the right side increases because the right side is doing more and more work of the left, right? So if you look at it this way, cardiac output versus right-sided preload, you might interpret this as an impairment of RV function. But if you look at right-side stroke work, that's not impaired. And the real mechanical impairment is on the left side. So what can we conclude from all of that? So first off, there's no theoretical reason why the Starling curve can't bend down, why there can't be a descending limb. In fact, the Starling curve actually does go down in certain stable, steady-state situations, like the experiments I just showed you. The question, again, is whether or not those circumstances reflect anything relevant to physiology or disease. There does not appear to be any physiological descending limb, that is, under physiological circumstances. But there may very well be one in disease. And we look at the Sarnoff and Braunwald experiment. Essentially, they gave an animal a heart attack, right? And the descending limb emerged. So for sure, in an acute impairment of ventricular function, like maybe in the early stages of STEMI, there actually is a descending limb. Does that happen in chronic heart failure conditions? Right? What about, remember these dashed lines over here? Should they still be dashed? So I don't want to take the cowardly way out, okay, and equivocate, but the answer probably is actually that it depends. Going out on a limb, pardon the pun again, I speculate that in chronic heart failure, where let's say left-sided heart failure, where the LV contractility is depressed and the afterload on the right side can get very high, then the descending limb, there's no reason for me to think that the descending limb would not appear. And I think it would appear for the same reason that it did in the Sarnoff experiment.